Let's talk more about factoring. Now we'll do special cases of factoring. Special cases basically means shortcuts, so faster ways to factor. For example, difference of squares we talked about in our last video. If you have a perfect square minus another perfect square, you can take the square roots of those bits, and make 1 plus and 1 minus. And you factor it. X plus 10 times x minus 10 gives you x squared minus 100. Because think about it, there's a 10x, and there's a negative 10x, and the 10x minus 10x gets you 0. And you can factor your solutions would be x equals negative 10 and x equals 10. And as I'm going through these shortcuts, don't forget that you can always just factor by your old methods. Like if you forget how to do this, well, you can take x squared minus 1 equals 0 and think about it like x squared plus 0x minus 1 equals 0 and just make it a trinomial. Now you want two numbers that multiply to negative 1 and add to 0, and those numbers are negative 1 and positive 1. And that's why this factors the way that it does. 1 is a perfect square. 1 times 1 is 0, is 1. So our solution is going to be positive and negative 1. Any even power is a perfect square. X to the 4th is really just x squared squared. And x to the 6th, or in this case it's y to the 6th, but anything to the 6th power, well, it's x to the 3rd squared. Any even power is a perfect square. So these are both perfect squares. I can get 4x squared minus 7y to the 3rd times 4x squared plus 7y to the 3rd. That one wasn't an equation, so there's no solving to do. This is not a difference of squares. It is a sum of squares. This cannot factor. No sum of squares can factor. There's things called the sum and difference of cubes, which we're not going to cover in this class, but it's another little shortcut trick you can find if you want to use that one. But for sum of squares, this one can't be done. If we tried to solve it, there's no number we could plug in for x to make this come out to negative 100. Like x squared can't be negative, so x squared plus 100 can come out to 0, so this has no real solutions. Next is a perfect square trinomial. This means it's going to factor into something squared, something times itself. Whenever the a term and the c term are perfect squares, and the b term is even, it's extremely likely that you'll be able to factor this and factor into a perfect square trinomial. There's actually a method you can follow to always know if something can or can't be a perfect square trinomial, but I think this is good enough. If this is perfect square, and even in the middle, if the b term is even, it's very likely. So we want two numbers that multiply to 36 and add to 12, and those numbers are 6 and 6. Well, x plus 6 times x plus 6 is actually just x plus 6 squared. So our solutions would be x minus 6 and x minus 6 twice. Sorry, x plus 6 equals 0, so x equals negative 6. That would happen in two different cases. So really negative 6 is our solution twice. What that means is that our graph is hitting a vertex is on the x-axis. Whenever that happens, whenever there's one solution twice, it means that the vertex of your graph is on the x-axis. Perfect square, even. If you take the middle term and cut it in half, that is always going to be how these factor if they are perfect square trinomials. The b term can get cut in half, and now it should check. X minus 1 times x minus 1 is, there's negative 1x is negative 2x. Negative 1 times negative 1 is positive 1, so this is how it factors. So my solution is going to be x equals 1. Factoring still only works if you're equal to 0, so add that 9 to both sides. This is x minus 3 squared. So our solution is x equals 3 twice. If there's y's tacked onto the end, then one option you have is to just kind of ignore them for a second. Let's just pretend like these y's aren't here if we want. And so now this is even and this is even, but I don't think this one actually is a perfect square trinomial. If I do 2x plus, well, this should be 2x plus 5, because 5 times 5 is 25. All right, there's the 25 I need to get there. But this gets me a 10x, and this gets me a 10x, and those two add up to 20x. So this doesn't actually factor that way. It's not a perfect square trinomial, even though it kind of looks like it, which is why you should always check. But suppose it was a perfect square trinomial. Let's pretend like it factored into this. It doesn't, but pretend like it does. Well, then we would go back and we'd tack back on a y. Because there's 25y squared, and there'd be a 10x and a 10x. So if this was a 20x, then it would work. 20xy, excuse me, not 20x. But it's not, so it doesn't. Quadratic form is when things have a quadratic form to them, but it doesn't look quadratic, by which I mean this is not a quadratic, it's x to the fourth. But if we had this, well, that's a quadratic we could factor, and then it's like each power got multiplied by 2. I shouldn't be putting all that in parentheses, so let me rewrite that. The powers got multiplied by 2. So here's all the powers that were in that in a basic quadratic. Then all the powers get doubled in this case. And so we get x to the fourth plus 5x squared plus 4 equals 0. The powers are being doubled here, not squared. That makes a difference. If these have, if this power is twice as big as this power, like here, it's 6 and 3, and then a 0 on the end, x to the 0, or 8 and 4. As long as if this power is twice as big as this power, and this power over here is a 0, then we have what's called quadratic form. And we just factor it as if it was a quadratic, then change the powers afterwards. So I'm going to treat this like it's x squared plus 5x plus 4 equals 0. And this factors into x plus 4 times x plus 1 equals 0. And now, because this was times 2, I'm going to tack a square onto these powers here. This factors into this. And if you do the distribution, x to the fourth plus x squared plus 4x squared plus 4, well, the 4x squared plus x squared gets you the 5x squared here you need. So now we have x squared plus 4 equals 0, and x squared plus 1 equals 0. And we solve these, we get x equals plus or minus 2, and x equals... Oh, sorry, neither of these can solve. There's no real solutions to either of these, because this became a negative 4, not a positive 4. Right, we would subtract a 4 from both sides and get x squared equals negative 4, and square root both sides and get x equals plus or minus the square root of negative 4, and there is no real square root of negative 4. There are other types of square roots of it that we'll talk about later, but this has no real solutions. It can still factor. It's very factorable, but it doesn't have real solutions. So this one, I'll change colors just to make these jump around a little bit for you. I'm going to think of it like it's this, and then factor into this. 3 and 1, I'll put the 3 here and the 1 here, and I'll make this a plus and this a minus, and I think that works. Yep. So what I'm really dealing with is 2x to the third minus 3 times x to the third plus 1, because 2 times 3 got me 6. And now if I solve this, I have 2x minus 3, 2x to the third minus 3 equals 0, x to the third plus 1 equals 0. These are solvable. You can only solve odd roots. So 2x to the third equals 3, divide both sides by 2, and x to the third equals 3 over 2. Cube root both sides, and x equals the cube root of 3 over 2, which is some number I could find. And here x to the third equals negative 1. Cube root both sides. And when I cube root, I'll get x equals negative 1. The cube root of negative 1 is actually just negative 1. Great. Let's move on. A quadnomial has 4 terms. These have to be solved by grouping. Grouping is where you cut it in half and you factor things out of the 2 halves. So out of these 2, I can pull out an x squared, and I'm left with 2x plus 3. Here I can pull out a negative 2, and I'm left with 2x plus 3. These 2 bubbles here have to be the exact same. If they are the exact same, the stuff in front of them combines into one parenthesis, and the remaining bubbles that were the same become the other. That is how that factors. We weren't asked to solve anything here because we don't have an equation, so we factor that. Now, Again, these are all just shortcuts. I guess this last one wasn't really a shortcut, just a way you have to factor it. But in general, these are faster ways of doing other problems. So don't let this confuse you into thinking you have to be looking for shortcuts or you have some method you have to follow. Don't make this hard on yourself. If x squared plus 4x equals 0, first of all, obviously, one of our solutions has to be 0. Because 0 plus 0 is 0. If there's no c term and you're equal to 0, of course we know x has to be 0. But if we're trying to factor this, you might be thinking, oh, okay, I want two numbers that multiply to, where's my, okay, I can think about it like this, maybe, I'll put a 0 here on the end. Two numbers that multiply to 0 and add to 4, and that seems kind of weird at first. What multiplies to 0 and adds to 4? Well, it's actually 0 and 4. So our other solution is going to be x equals negative 4. But again, this is still harder than it has to be. Pull out a GCF of x. Now we know here, x is 0, and from this one, x is negative 4. Always pulling out a GCF first, always just thinking about how can I keep this simple is worthwhile. Look at the problem and just try to analyze what could x be, what could x not be, how can I use that to factor. Finally, I want to talk about what we're doing when we're factoring. We're actually finding roots. If I were to graph f of x equals negative 2x squared plus 8x minus 6, well, my AOS is 2, and f of 2 gets me 4, negative 8 plus 16 minus 6, which is 8 minus 6, which is 2. My vertex is the point 2, 2. So I'm going to draw on a quick set of axes here. If it's 2, 2, and I know this graph is pointing down, I'm going to give myself a lot of room up here. So put the point 2, 2 here. If I factor this, I'll have negative 2 x squared minus 4x plus 3, which is negative 2 x minus 3 x minus 1. Well, what I just found are the roots. Now I know that if x equals 3, if I do f of 3, I'll get out a 0. That's here. And if I do f of 1, I'll get out a 0. It's here. When you're factoring, you're finding roots. And I know that the graph is going to point down because of this, and I could find a y-intercept. I know it's negative 6. Here's my graph. Here's my roots, which can come from my factors. It's a beautiful little cycle here. That's all.